Dr. Debabrata Goswami is a professor with the Department of Chemistry, IIT Kanpur since 2003. He obtained BSc from Jadavpur University in 1986, MSc from IIT Kanpur in 1988, and PhD from Princeton University in 1994. Before coming to IIT Kanpur, he was a faculty at the Tata Institute of Fundamental Research, Mumbai, for 5 years. He did postdoctoral work at the Harvard University and Brookhaven National Laboratory. He is Wellcome Trust Senior Research Fellow and has won many awards and honors, including prestigious Swarnaja.
So this is more for the start of the students. Generally, when we were growing up, spaceship or space, the final frontier, was the main aspect. And as you can see, those are all wonderfully done through Newton's laws. And so whenever we used to be amazed with the concepts of space and everything out there, celestial bodies, they are wonderful, but quantum mechanics have no role to play there. When, on the other hand, we got introduced to this idea of quantum mechanics, in fact, I'll tell you how it all started. We came to the first year classes. At that time, it was the old quantum mechanics, which was the Bohr model which was being taught. All mathematics, we still knew that the atom was a sphere, and had a perfect size. So you could tell the radius of the atom, and so on and so forth. We come to our master's level. First class, I happen to be an alumni at the same place now I'm teaching, IIT Kanpur. The teacher comes in and says, throw away whatever you have learned until now. There is no hard and fast radius of an atom. Just start off new. Let's start over. And that's where the probability and the entire concepts of how atoms and molecules can be related to wave functions and things like that were more and more embedded in us, and we started to enjoy the concepts of probability. And this wonderful little thing, which is thanks to net that I have just picked up, is a wonderful visualization of how probability concepts in quantum computing or quantum aspects can be wonderful. So this is the basic concept, and this also is a little bit of a lifesaver for me, because I have to sometimes keep on justifying how do I hold a position in the chemistry department, although he did not read that I am actually member of the other departments more than my parent department. But still, I have to keep on justifying that there is a molecule involved somewhere which is a harmonic oscillator, which essentially then is distorted off enough that we can put in enough quantum mechanics and physics and talk about it. So here is the story behind this. And the other important part here is that we generally break it down into two parts of the Hamiltonian, one of which is the intramolecular part, which is the one which we treat very carefully in classes and everywhere, where we basically explain how the system as a spring can be looked at, and how the bond sizes, bond length and everything is changing, how the atoms are coming closer and things like that. And the only difference I keep on telling sometimes is that when you talk about more than one nuclei, then you are entering chemistry, otherwise it's all physics. So that's where you have the nuclear vibrations, and these vibrations are the reasons for your bond, and this gives us the richness where we can look at quantum systems and try to see if we can do more and more things with it. The other part of the story is that it also has a simultaneous translational motion, and this translational motion is something which is often not to be worried about, because this is something when we do spectroscopy or any of the studies that we do does not affect us. Most of the time we go into our frame of reference where this translation is essentially frozen out, be it be some of the studies we do. However, in quantum computing, as we will discover here, this is a critical step which is also necessary, a control which is needed. So, except this one or two slides, I have removed all the introductory ones. I could not remove Richard Feynman's slide, which says that, we cannot make the mystery go away by explaining how it works. We will just tell you how it works. And this was basically the principle which was also told to us when we were beginning the concept of quantum mechanics. that you don't really have to visualize everything. It becomes more and more complicated. You just see the answer and try to backtrack it. And today when I teach quantum computing in a class which is 50% computer scientists, I tell them not to worry about quantum mechanics or the physics, just see that they are matrices and you are the best in solving matrices and you can do it. That's the way you often look at it, and it works. So it was the greatness of Feynman, who as a physicist could actually understand the concepts of computer science, but it also came because Deutsch came to him with his problems, and so this collaboration is something which is the reason for the birth of new fields. And as we stand here, I think it is very important that we keep on realizing that the collaborative research is one of the best ways to go ahead for the future directions. I generally am an experimentalist, although that's why I mentioned in the very opening sentence statements that I do most of this part because the theorist hat is borne by me nowadays. All the rest of the members of the lab are essentially experimentalists. And so we work in femtoseconds. One of the reasons why 10 to the power minus 15 seconds happens to be very important for chemists is because they are not interested in attosecond, by the way. Though physicists are very interested, but they are not interested. It's because vibrational time period is roughly in this region, is roughly in this time scale. If you go faster than this, then the usefulness of vibrations or anything related to that doesn't become any more useful. So you can map out, let's say, an atomic orbital, but that's about all that you can do. You cannot do anything more interesting with it. That's why attosecond is more physics, and femtosecond onwards is more chemistry, if you look at it that way. And if you want to go to biology, then it's longer timescales. Although vision, for instance, the process that we are all looking at each other gets triggered within 6 femtoseconds. So this is the concept where control, which is one of the major areas or major interests in this process, is particularly lying in the fact that had we get the control over exciting one single bond so that we could control the energy right there, we would be able to do wonders. And that is the basis of the chemistry, which is that you make the bond vibrate, and you would hope that the energy, if it was able to be sustained there, would have broken. But unfortunately, in these coupled systems, they all move into other directions. So they are all within a few femtoseconds. They are all the entire molecule vibrates. Now, this, in some sense, is very, very complicated in terms of quantum computing, because in quantum computing, if we would like to get computation going, we would like to keep a track of how things are happening. Now, this being a randomized situation, that you have a vibration or the energy being localized is now getting delocalized, it is almost like having a concept of coherence going down to decoherence. And so this particular process is something which always creates a problem in terms of quantum computing. So one of the aspects of quantum computing in rephrased term would be to just stop this process of randomization, which is decoherence. And so one of the areas or efforts in the first part of molecular quantum computing has remained in trying to stop this process of randomization or decoherence, also popularly known as intramolecular vibrational relaxation, because this is the same molecule where this is happening, and that's why it's looked at it this way. And NMR principles, which is often used, essentially start from these, but here we'll be concentrating on optics, and I'll at one point also mention why you would like to have optics as the better option. So this is our typical laser system, how it looks, and as with every situation, whenever you start off with a particular area, which is the femtoseconds, now there are many other things that you can do, and this particular talk and the focus of this research or the center is connected to the quantum computing part, where we would like to see how our efforts on molecular quantum computing has anything to be of excitement. So with that, let us now look at the problems in part by part manner. So the best thing is to try to start off at the very simple level of a 2 level, and everybody would love to have that, in our particular case, even if we start off with a single two-level system, we have the other option when we use light to have a multi-photon interaction versus a single photon interaction. Now, this process has its benefits because most of the molecules has this interesting situation which is known as an ionization threshold, which can be treated as a region where you have only two levels. So if you go to the ionization threshold and beyond, the molecule is bound to break down. And so you essentially are left with two levels. One where it is stable, and the other where you are basically going to break down the system. So if you look at it that way, then you can have the situation where you are going to make the system go to a breakdown condition, or which you can achieve with one single energetic photon, or you could put little bits of photon in such a way so that they all add together coherently to give you the final solution. Now, as I was posing the problem to you, you could perhaps understand that quantum mechanics and all those roles put together, multi-photon approach has a much more control built in as compared to a single particular excitation process. Because a single particular excitation process is a definitive process, all right, but the control offered by that, the parameters available in this is much less. So the system interaction in this process of multi-photon interaction is much, much more rich compared to when it is done in a single energetic photon process. So while breaking down of a system as a hammer would just mean that you just blast the system away and you don't care, it's a big hammer which will do the job. If you would like to see certain aspects of this breakdown process which is under your control, you would rather want to have these little packets of light which are being controlled in your own way by interference or through some coherent phenomenon, so that you can always recursively go to a point where you are able to talk about how the system breakdown at the end can correlate to some methodology of your computation that can be related to. So this is one of the tricks that you can start off with. Although there is nothing known as an ideal two-level system, you can construct a situation where you have a ground state where every molecule can exist within a statistical limit, and you can have an excited condition where when you make the system go up to, it will anyway break down. And once this breakdown process is achievable through small little tinkering of photons, then you will be having more and more control over the excited process that you are looking at. And so this is one of the principles which is used. Mathematically, it essentially means that you are going to solve a matrix formula where your control parameter then would be the field which is going to be put as one of the diagonal elements. Now, these are places where many different approaches can be used. This particular approach is using a very simple scheme where I am using a pulse where the number of cycles are many, so that you don't have to worry about the cycle effect within the electric field. Nowadays, with attosecond pulses coming in, within a field, number of cycles are also becoming more and more important. But the basic theory of signal transaction also still remains here. We have done some very recent research where we have shown that irrespective of how short of a time you go down in, so in terms of going down to, let's say, attosecond pulses where you can count the number of cycles within that pulse, your envelope profile of the pulse is still quite important in determining the outcome. And that is a principle of signal information signal processing, where it says that any well-behaved signal, if you know a certain part of it, the rest of it is already defined. So those principles all work. There is no surprises here. Only thing is, you are trying to see if you can control the interference or the process in which they are getting connected to give you the excited state. So one of the options is to actually use the field in such a way so that the field within the pulse is changing in a particular way. So for example, if you change the color of the field, color of the laser within the pulse, then what will happen is it will cycle slower in the beginning or faster at the end, and vice versa, depending on whether it's going from red to blue or blue to red. And this could perhaps make a big impact. And this is one of the things which was found out, that you could in fact have, this is one of the generic pictures which makes it more easy to understand, where it shows that if you have, now we are talking in terms of only the population or the amount of one of a certain kind. We are not interested yet in what happens of the coherence of the system. Now, the reason why these matrix pictures are very useful for as a student, it's much more important to understand, is that in the matrix picture, the best thing which remains is the diagonal elements talk about the shear population, which is all right. However, the off-diagonal elements preserve the coherence of the system, the connectivity of those states that you are looking at, and their phase connectivities. And therefore, it's very important to sometimes look at their off-diagonal elements. Although off-diagonal elements are not directly observable, they have an impact on the overall processing of the system. So, but however, if you are only looking at the diagonal elements, you can see that by using a frequency which is changing within the pulse, where it goes from below the resonance to a resonance to past the resonance, you will be able to excite the system completely to its final state. And this is an important achievement because in most cases, as it was shown in the earlier talk also, you would be essentially seeing an oscillation between the ground and excited state, because once you put everything up there, the same pulse or the field can bring it all down. And so you will essentially go through a cycling. However, in these kinds of situations, you don't see a cycling. You put it all the way up there and it's going to stay there. And this, by the way, is a very well-known theorem which is often also used in NMR and other fields, which is known as the adiabatic principle, where the motion, the field is changing in such a way so that the applied field is strong enough, but strong enough to make the population go all the way up there, and it's not having any more time to come down, because by the time it has gone up there, the available energy color has changed. The frequency is no longer the same. As the frequency is changing, it's only here, up to here, that the resonance is there, but beyond that, the resonance is gone. So even if you are here, you will not be able to push the population down. That's the basic way of understanding these principles. So these are the underlying pictures. The only reason I was sweeping through them is that there is a consequence of all those calculations. In doing calculations, there is one beautiful thing which you can do, which you cannot do when you are an experimentalist. Since I do both, I can tell you. As a theorist, you can always look up things which are not observables. For example, as I mentioned, the off-diagonal elements of a matrix is generally not an observable, at least in the same frame of reference. However, when you are doing the simulations or calculations, nobody is stopping you to not look at them. And so we can look at them and make some wonderful conclusions which are very logically correct. It turns out that you can apply whatever is known in age-old spectroscopic principles, which is known as the Kramers-Kronig relationships, where all the absorptions are composed of the real and the imaginary parts. The real part is known as the dispersion or dispersive part of the absorption, and they actually have a profile which essentially shows you how they are. One is a derivative of the other. So if one of them, the absorption lines are essentially a Gaussian, for instance. So if you take a derivative, it will be something going up and down, and it will go through a minima at the peak. So that is, and physically, that is how a refractive index of a system changes. And those of you who are all familiar with these cutting-edge research areas which come about saying that superluminal velocity of light and all those things, those tricks are being played because the refractive index of the medium is changing because of when the propagation of light is happening. And this is nothing surprising, it's all happening because of the impact of the imaginary part when absorption is happening, the real part where the refractive index changes are happening also simultaneously is going on, and therefore you can see that effect. And if you are tracking a particular light wavelength at that time or under that condition, you might see speed of light faster than speed of light travel and all those phenomena coming. So it's not surprising, it's just very simply understandable from all these simulations when you can look at them. The other thing, as I just mentioned, is that the Rabi flopping, or the population going up and down, was first observed in the very beginning of these principles by Rabi, who also got the Nobel Prize for that. This is the cosine squared flopping, and this is only happening due to absorption. So this is the part which is happening due to the imaginary part. However, when you go to the adiabatic process, where the frequency is changing within the pulse, the coupling is through the dispersion part, and there is no absorption. And therefore, when we are looking at this kind of processes, there is no population flopping going on. It's just a simple process where the population just goes into the excited state and just stays there. And this is one of the interesting principles that you can learn from these kinds of theoretical understandings, where by just dissecting out the calculation or the process how it is being done, you can understand the logistics behind it. So one of the importance of these kinds of studies is to realize that this has a quantification of two-level character in a multi-level system, because now what you can think is that you have a large, as you saw in the last talk, there was a visualization that these grids were being made. So you can think about your entire matrix be a large matrix where you are making grids of two levels. And now all these grids of two levels are the ones which are now coupled. And these qubits, these are your qubits. Now you want to see how these individual qubits are going to interact. At the very first step, what you do is you try to rediagonalize the entire matrix so that only certain of these survive. And the simplest one, which is often done, is to make only the diagonal ones survive and the rest of them are made zeros. And when that happens, all these connectivities that you look at, those are the ones which can tell you about a two-level characteristics of a multi-level system. And it's very important for molecules, because molecules are never two-level. But you can make a two-level approximation based on these kinds of manipulations, which are perfectly allowed, because all you are doing is matrix diagonalizations are nothing but frames of reference changes. So it's not an unacceptable parameter. The other thing is to understand that the off-diagonal density matrix elements switch from real to imaginary when the excitation process changes from being resonant to completely adiabatic. And this is the reason why you can see a complete inversion process happening in one case, whereas it is Rabi flopping in the other case. I once more highlight the difficulties of using, or the challenges of using molecules as qubits. First of all, the true two-level picture is something which is often which we are hunting for, and that's the reason of this entire few slides that you saw just now, where we were essentially trying to demonstrate true two-level nature of molecules, because all real molecules are always multi-level. And the increased dephasing times of the states which are to be used at qubits is a major problem in molecules, because the time scales involved are very fast. Those are all in femtoseconds. Now there are two advantages of having faster. There's one advantage of having a faster time scale, and there is a corresponding disadvantage of having a faster time scale. Faster time scale helps you to do many more cycles within a given period of time. That's one advantage. However, the bigger disadvantage, which is currently staring at all of us, is that the more cycles that you can do, the faster decoherence also you face. And so if you can get your decoherence times to a controllable point that is comforting in terms of doing a cycle, then you can use molecules in those time scales. Now, I just told you before that attosecond is not a good idea. In fact, that's one of the things which the reason I got delayed was also that in the middle I tried some attosecond studies, and what I found out was it is indeed true that the chemists have been correctly sticking out for the femtoseconds, because in attoseconds things don't work out the way we are looking at it here. And so we don't have much of a choice. The only choice we really have left with us is to make the process go slower, such that we can do the cyclings within vibrational timescales of the femtoseconds, where cyclings of femtosecond means within 10 to 100 femtoseconds are allowed, so that a particular gate is executable, and then we go to the next step. And that would be the dream situation, because you can within a picosecond or 2 picoseconds, where the total population dephasing of system comes down, you already have finished many cycles of operations. In NMR, on the other hand, the time scale of these processes are so long that you in fact have to reset your qubits physically in order to get back your computer. And that can be another pain in the neck. So there are other problems, but this again is a major problem in NMR also. So one of the approaches to do this is to basically look at it in two different ways. One is a temporal one, which I just was talking about. The other one is a spatial approach. Now, spatial approach is the place where I mentioned that, you generally only talk about a Hamiltonian, which is the vibration or the other kind, but you don't talk about spatial. But if you look at the spatial type, then it's important because you can isolate or control molecules such that they can be made to interact under experimental discretion. And already people use molecular beams, and one of the extreme examples was the last talk where you use single molecules, where you are able to use atom traps so that you put them under individual conditions, you manipulate each of them, and you pick and choose your time as to how you are going to make them interact. Now, although that's a wonderful dreamlike condition, it is difficult to, it is one of the most difficult experiments, and only a few labs in the world, I think, will really attempt to do those kinds of experiments. NIST is a wonderful example. It's a different story, but generally speaking, these are very difficult experiments to attempt. So, one of the other ideas that could perhaps work was to try optical tweezers, because optical tweezers are things which can happen at condensed phase. And if you go down to condensed phase and if you can get things work, then it will be interesting. Typically, however, optical tweezers are used with laser light which are continuous. And we all know that whenever we are trying to send out information or communicate, only we need some information bit to go through it. And therefore, we ended up developing pulsed optical tweezers for this purpose, which is which seems to have a lot of interesting effects. So I'll get into that. Before I finish my part on the little bits of theory, I can sort of impress you a little bit that although the students are toiling away in the lab, I am also not just wasting time. Many times there are matrices which are large enough and very complicated enough which have to be broken down and looked at. So there are some justifications in there too. But here is one of the last bits to get out of the calculation part. It was an interesting case where we were able to show that just by using simple pulses where the frequency was modulated slow enough, we were able to hold the population between. So basically this is an interesting case because we are having a 50-50 population where the coherence between the states are 100% maintained. So basically it's a condition where the relative orientation or the phase of the molecules are well established. And this is the condition which we are able to attain by using these kinds of principles only for a brief amount in these cases, in these scales, for a molecule of anthracene. This is again a model situation because in reality you don't get only these few states. Although Peter Felker and Zuel were the people who had done these molecular beam experiments where they had shown that under their experimental condition, they were able to only couple a few states. And so under this condition where there are only a few states available, then you can have a situation where even to a tune of 10 to 20 picoseconds, you can keep a state coherently coupled within the experimental conditions. You can come up with shaped pulses which will do the job for you. Here is an example of this. If you can take a pulse which essentially goes up to resonance and stays there during a period of time and then turns it off, it is one of the ideal cases where you can actually get a population control over a large period of time. Unfortunately, these kinds of shaped pulses have yet not been managed to be demonstrated because these kinds of pulses and the power levels that are being asked about is even in today's present day technology is not yet possible to be done. Although shaped pulses are possible, but the intensities necessary to make these kinds of things happen are not yet possible. The other part of the problem which happens is that although at low energies or even at spectroscopic studies which are done at low energies, molecules behave in a certain way. When they start being treated with very large intensity lasers, they behave in a very different manner because they are now a coupled oscillator problem. And so their states are no longer the states that you started off, and that's the principle of rest states, where photon, matter, radiation, all these interactions give rise to new distribution of states which are not the same that you had originally started thinking about. And therefore, until now, there has not been any demonstration of these kinds of experiments. Theoretically, however, they are very nice. It's not just me, there have been other people who have also theoretically demonstrated that these studies can be done. And in fact, if you can extend them, you can propose to Grover that we can make equal superposition of bright states, equal superposition of states which matter in this case, by simply using pulses of light, which will then put all these states at equal superposition. Unfortunately, again, the same problem exists, that these decouplings are not that easy, and although we might think that the bright states, quite a large number of bright states can be made to have an equal population by these kinds of principles, is not yet experimentally demonstrated. Let me now quickly get into the spatial knob case. So the spatial control is one of the things which we will be talking about. Typically what happens is that you can use photon flux to sort of stabilize the system. And this, by the way, is similar to the tractor beam principles in spaceships. And here what happens is that you have the photon flux, which in this case is being focused, and as they are focusing, particles face different gradients of the light going through them, and these are typically partially transmitting, at least. I mean, they are not completely reflective, although in principle you can have a completely reflective particle also get into traps. However, it's much easier to explain particle traps with particles with beads or any of these particles which are supposed to have larger refractive index than the medium, because then they get pulled into the focal volume and you can just quickly get it trapped. So it's the spatial profile, which is a Gaussian profile. These are the Gaussian profile beams where you can have the laser bend through the particle, and this bending helps you to bring the particle into the focal point. And if it is having an opposite refractive index, in fact, on a similar ground, you can chase away particles. So as you can trap a particle, you can also chase it away. So, but mostly remember that these are all single beam optical traps which are being talked about, and the pioneer of this field was Ashpin, who first came up with this principle. However, one of the most important things to remember here is that the gradient of the field cannot be zero. And so if you have a flat top, almost a rectangular profile beam, then you will not be able to trap the particle, because you need to have this criteria to be satisfied. So now what we have done here is that we have used a pulsed laser. Now why is pulsed laser important? I already justified you in terms of quantum computing, that you would like to inform a particle which is getting trapped so that it can do whatever you would like to do with it. One of the ways of information is using different wavelengths, but then again, different wavelengths, which is WDM. WDM technology on using an optical trap will not quite work, because you are going to use a single beam to do that. So if you are going to use the same single beam principle, then the best way to have something to do with it is to do a TDM kind of a principle, which is like having a pulse laser. So the pulse laser in some way can transmit information which can be utilized. Now there is another selfish motivation of having pulse laser to do the trapping for you. It also makes it visualize much more easily. Typically, a trapped particle is looked at by its scatter. It's just like, we are all looking at each other mostly because of the minute particles, scatter light which are coming out. Our eyes are extremely good in processing them and letting us know who is sitting where. Similarly, when you trap a particle, the light coming back from it is being looked at, and that becomes brighter than the rest of them. So here is, for example, the case. that you are able to see the trapped particle, because the little bits of light that is extra coming, because it is now localized, you are able to see. However, if it is a fluorescent system which can get excited, so here it is actually, it's a dye which excites, which is getting excited by 2 photons of the light, and then you can have fluorescence coming out. Then it is a much brighter condition. In fact, you can turn off your bright light source and you can see it completely in background free condition. And so watching a trapped particle becomes much easier. Now that also means that as you make as it becomes easier and easier to observe, you can make your particle size that you would like to look at smaller and smaller. And so by doing this technique, we have gone down to about 16 nanometer particle size, which, as you can see, is much smaller than the diffraction limited spot size of any light that we are now talking about. These are all done with 800 nanometer wavelength, and so technically you are limited by the 800 nanometer size limit, which is the diffraction limit sizes that you can think about in terms of the particles. But we can go down to about 16 to 20 nanometer sizes, because we are using this principle where we are using the background free illumination of the fluorescence which is coming out. And there is another important reason why you would like to use 2 photon process, not a single photon. One of the reasons is that if you use single photon, the possibility of other particles getting excited will be much higher, because you don't need that much intensity to produce a single photon process. So the background of all the immediately coming close by vicinity particles would be reflected in your focal volume of what you are trying to see, and so it will be difficult. You will be seeing streaks of comet-like situations if you are using a single photon condition. There is also another major reason why you wouldn't want to do a single photon fluorescence while you are going to do an optical trap. That's because your optical trapping principle is based on a very simple principle where we assume that there is no loss of the light which is being, when this simple theory is being developed, the principle which is being thought about is that there is no loss of light as the principle is happening. And so if you have a single photon process, then there is enough, the chromophores can absorb enough light that this simple principle that there is no loss of light can no longer be applicable. Also, it can lead to many other principles, many other problems, like as absorption goes on, so the system can get heated, and the moment the heating of the system keeps on happening, then trapping becomes more and more difficult, because the particles will have higher and higher probability of moving, because it's now is becoming temperature is going up, so its Brownian motion principles go higher. And so 2-photon process is a process where the probability is so low that it will only happen where the flux of the photons is very high, only during the focus point. And the intensity of the light can be increased when light appears at a very short time period. And that's why with femtosecond laser, it's a very easy experiment where you just very little light to excite and you are able to see trapping. Now there are some very interesting physics that can be looked at. In fact, first years also, when we start teaching freshmen, we start teaching by particle in a box principle. Now, particle in a box principle, when we start by teaching, we say that the reason for quantization comes because it is we are putting the boundary conditions. Here have a condition where the boundary condition is coming because the light being there or not being there. And so that can be another. It is not going to be quantum. Definitely not, because we are not talking in those size scales. When we go down to 16 or 20 nanometer sizes, people can still argue maybe a little bit. But generally, this is a very different case where having a well versus not having a well can be looked at as having a boundary condition being there or not being there. Simply speaking, translationally, what you can see is that the stable trapping over time will happen as long as this particle does not get enough time to move away when the next pulse is going to appear. If it has moved away too far, then it is not going to be seen when the next pulse of light appears at the same spot. So this time period, the frequency of the laser has to be in the region of a few, in the region of a megahertz or so, 10 to the power 6. So if within about a microsecond, if a pulse comes, then you will be able to see the trapping happening. So these are the few parameters that can be looked at, and this can be seen. What we have managed to do that is that we have managed to get latex nanoparticles, which are otherwise very hard to trap, which we have managed to show by these techniques. Now I want to switch gears and talk a little bit about control here. Because as I mentioned at the very beginning, control is one of the most important parameters here. Now, I was trying to bring this idea from before also, that when we talk about molecules, we are talking about things which are very to be handled very carefully. They are not to be handled as somebody like a Terminator would do it. And so we have to be very careful. It's not a jackhammer principle here. That's the reason why a multi-photon process is perhaps better than a single photon process in these cases. And so what we would like to do is to use our control knobs in a much more useful manner rather than doing it. So one of the issues which becomes important in this control world is to find out control knobs which will be independent of each other. Because if you have knobs which are going to interact within each other, then if you are going to get to a certain gate based on many of these knobs put together and they are mutually interacting, then you have no knowledge of what you are finally going to arrive at. And therefore, I mean, it can be, but it's a much more complicated mathematical problem than if you have well-defined activities of these controls which can then be used simultaneously one after the other. And in this context, we had already used frequency chirp. What we thought was that we would be using laser polarization as another control knob simultaneously and see what happens. Now here are certain basics about lasers. Typically a laser like this that I'm using as a pointer is a CW laser, as we call it, is almost a delta function in wavelength, but in time it's continuously there. That's why it's a CW laser. On the other hand, femtosecond or short pulses, as we talk about, has very wide bandwidth or lots of wavelengths, and so it is very poor in terms of wavelength selectivity. Otherwise, it's very good in time. Now, when we want to actually do something like change the property of the pulse in a programmable fashion, one of the techniques which I developed as a PhD student years ago was to use a programmable modulator. This is an acoustic modulator, which was placed in a Fourier geometry such that the time didn't matter at this place, and we were able to put the different frames of our RF pulses, and if we were able to collect the right pulse properly, then we would be shaping the particular pulse that was necessary. Now this is a interesting technique and it's useful, and this is corollary for those who are in the field. They know that this is corollary to a similar principle which was developed by Weiner and Heritage, who are senior to me a lot more. But one of the advantages of this technique is to be able to do almost a background-free condition of pulse shaping, and so a lot of calibrations can be avoided. And there are many other advantages of this. One of the most important advantages is that the repetition rate at which a new pulse can be generated in this technique is much, much faster than any other technique. However, the biggest drawback of this technique is that the efficiency of this entire process is quite low. So for doing molecular level processing, which needs a lot of power, it is one of the places where you have to somehow manage to put in is much before another amplifier, so that you can reasonably amplify the laser again so that it can do something useful for you. So that's one of the techniques, and Phil Buxbaum and others have utilized it in similar manner after we had demonstrated how to do it in terms of amplification. We had recently done some more modifications with all reflective techniques because as we went down in time, it was necessary to go and beat the dispersion. And there are some technical details, we need not worry about it. But although much more sophisticated techniques can be used, it turns out that for many cases, having a simple condition where the frequency is going to change from one color to the other in a linear fashion is good enough. And for these kinds of linear fashion experiments, all you need is a grating, is essentially some gratings and lenses. So for those techniques, and these are very commercially viable because many of the laser equipments come pre-built with these kinds of situations. So in some way what you are trying to do is you are trying to sort of work with a commercial laser and just change certain parameters within it rather than rebuilding an entire system for you. And so it turns out that this is a much more accessible way of doing experiments. And so when I started my career, although I developed the other technique, I ended up doing most of my work with just these kinds of shaped pulses, which are essentially taking a grating and a mirror and changing the separation in such a way so that the colors of these pulses within them are changing, and then we use them. So this is a molecular beam chamber. The only advantage of this particular system is to make sure that the molecules are coming in a laminar flow and they can be addressed individually to some level. It's not like a cold atom or anything of that sort. This can be used as a route to get there, but in this particular cases, we are only using a burst of molecules which are having a certain velocity ratio component which have been selected through many processes of expansion, and then in the region of interaction with the laser light, we have a pretty well-defined molecules conditions experimentally. Under this condition then, we can apply a laser field which is having different colors going, and then we added the other part, which is to say that we will be adding the polarizer part to it. So first we looked at what happens when we change the frequency component, and somehow we were lucky that we picked up, well, because at the end of the day they have different products. As I mentioned, that you can generally visualize these conditions as molecules which are under a condition, left alone they will be somewhere, and once you push them up to a certain point, they will just break down into certain channels. So the idea here is that this molecule was able to go up to a condition where the products were of certain kinds. And those products came from different directions. It was possible to manipulate them very heavily by using the pulse condition. So here it is one case where we are just using the pulse as it is. There is no change in the pulse, and we see a distribution of all the fragments that are possible to be gotten from the molecule. Now this is a case which you will get irrespective of what you are doing with this molecule. Now when you then start applying different conditions, so this is the case where you are making the pulse go from red to blue or from blue to red, then you will start seeing that your distribution of these resultant fragments are very different. And so by picking up how these fragments are developed, you can create a map under what condition what you are going to get. So basically by looking at the different frequency components, you can do this. And you can come up also with a mechanism as to why certain fragments are favored versus the other. So for example, red to blue is supporting this fragmentation channel, whereas blue to red is supporting this fragmentation channel. Okay, now we then started looking at what happens if we then change the polarization of the system. And we did it simultaneously as well as independently. So first we did it independently, and then we looked at it simultaneously with the chirp and the frequency. And so this is a case where it is being looked at independently. Only the polarization is being looked at, and what we see is that as the polarization changes from being circular to linear to circular to linear, or and vice versa, you could see that it goes through oscillations. Whereas if you change the frequency as well as the frequency content as well as polarization, then they are looking quite different. Okay, so initially we were a little bit worried that they are perhaps similar, they have common grounds, but we were quickly able to understand that the two parameters are mutually exclusive here and one does not play with the other. And so that makes chirp affects the ratio of the individual fragment ion pattern, whereas the polarization affects only the overall fragment ion pattern but not their relative yield. So the relative yield part is untouched by the polarization. So that's why you could have these two be directly used simultaneously. And so laser polarization and laser pulse chirps are mutually exclusive control knobs. And so this is a very interesting situation because had they been connected, it would have been very complicated to work with this. But as of now, this has become something which is not connected, and so we are hoping that something more interesting can be taken from there. Before I switch gears, we should. This is a Dilbert cartoon which came out as early as 1977, where he used to make fun of everything. But this concept as to why should we only go ahead and pursue quantum computing also remains as one of the areas which is perhaps more useful to nerds like us who are always thinking, what next can we do? But on a realistic ground, let me actually show you an experiment where there is a reason to believe that these kinds of controls have more important consequences than just this. So I'll give you two quick examples. One of them is coming from my home department, chemistry. So here is a case. I don't know. This is some cyclopentadiene, this molecule. It has some configuration, chair, boat or whatever. Now the point is they break down to two different cyclopentadienes. And so this is a dicyclopentadiene. Okay. It turns out that this can be done. This, by the way, when we were in schools or when those who are in colleges here, they might know that this process is a very famous process. If it goes in the forward direction, this is known as the Diels-Alder reaction. This has been discovered way back in the 60s, and it's a very famous experiment. It's all thermal. It in fact happens only at the ground state. Okay, this is a ground state based scenario, and this is a cyclization process, and this is very important because it turns out that this is a resonance enhanced process. The electron cloud gets enhanced by, there is a stabilization because the electrons are getting delocalized and blah, blah, blah. Whatever the story is, the end of the day principle is that this process of cyclization is a very facile and useful thing, useful step. Now this is a much more clean experimental setup because what is happening is that those fragments are only two. We don't have to worry about too many fragments, but there is a correlation between these fragments. One goes up, the other one goes down, and so there is a very strong correlation between them. And if we don't use any process which is dependent on the breakdown of the system, for example in second harmonic generation or just by looking at the dimerization process, then what we find is that they follow exactly the intensity parameter. But because as you change your sweep or the frequency content, the pulse width also changes, so you can actually see a perfect parabola that way. However, when you use the molecular system, only one of the sides, which is on the negative chirp, shows a major difference, major deviation. That means this is getting highly influenced compared to the other side. This is exactly the way the pulse width is changing, but the frequency content really makes a big difference when it goes on the other side. So just to influence you with the fact that even if we do quantum computing, we have to impress upon our funding agencies that we can do other things than just saying that someday shift will happen and we will all die. That's not just the entire story. It turns out that this has a huge impact on other areas of experimental science, including microscopy, where You can use multiple pulses that I was just showing you with high repetition rates, and you can use them judiciously enough with a proper spacing here. So if we actually, instead of using one single pulse that is generally used, we use two pulses where the pulse separations are in our control, then what we can do is that for cases where the chromophores or the image is blurred because of many other images coming at the same place, we can saturate out one versus the other. This is how it looks like. Saturate out one with respect to the other and can get a clear image. So here is the image. So depending on what delay of the pulses we use, we can pick up one versus the other and can see a greater contrast microscopy. In fact, this is very interesting because by using time, we are in fact now going to a resolution which is again much better than what light would have otherwise provided us. So we are getting into, so this is an area which is known as super resolution microscopy. A lot of work has been going on in this direction. This is our direction of applying to it, where we have used pulses of light to come through and do these kinds of experiments. Stephen Hell and others in Max Planck have been actually using it by different techniques of using the beam profiling. We have just used by simple pulse shaping principle. Again, this is no fancy. We are just using two different reflecting materials where they have a separation, and we are just playing with their separation, and we can produce pulses of different delays, and that helps us in producing these kinds of contrast images. There are some other stories which I think I have already talked about it here, so I'm not going to repeat it here. I'm very thankful that you have managed to give me so much time to talk about all the different kinds of research that we do. This is one of the most recent work of ours which has come out from the physical chemistry, where we have talked about the molecular motions in fluorescence and optical trapping through using spatiotemporal approach. So we are just trying to coin the term of spatiotemporal in liquids in order to make sure that this becomes an important aspect in the future research. With that, I'd like to thank you for your time.
We have one quick question.
You have worked on N-profile benzene. How do you choose a particular molecule? Before choice, is there any simulation which you can test before doing the real experiment?
Simulation would be a good idea, but most of the cases these molecules are way too complicated to get legitimate simulation. So what we look for is that if there has been any earlier experimental work of similar compounds. So this particular compound was not done before, but there were similar compounds of other kinds where there were trends of branching ratio differences. So by looking at the fragments, we could say that there were different branchings going on. So we were having a hunch that maybe there are different mechanisms in play. So we looked at this. It turned out to be in our wavelength region. The other ones were not in our wavelength region. It's not that we didn't want to do them, but those were not in our wavelength region. It turned out to be in our energy range that we could address, and we were lucky that it did go in the direction that we were looking for. This one is a purely experimentalist approach.
Okay, so thank you very much, Professor Debabrata Goswami.